Hello students, this is the physicist and we are going to discuss the flow of electrons in a current carrying wire, both for AC and DC. But before we go on to the direct analysis, I just want you to brush off your concept of the electric field created by a uniformly charged ring along its axis. So let's take the a uniformly charged ring which is negatively charged. It's a ring, and let's see how the electric field looks like along its axis. So let us take the axis like this, right? Now let's suppose the center is at O and we choose a point P, right, on the axis. Now we will try to understand how the electric field on the axis looks like, or rather we are trying to understand what effect will it have on an electron placed at point P. This uniformly and negatively charged ring will have some effect on an electron at point P, which is on the axis of this ring. So what kind of effect will it have? So to understand that, imagine I will just choose a small portion of the ring at a point called A. Now if I want to see the effect of this negative charge dq at A, right, it will have some small charge dq there. The effect will be like this. Yes, it will try to repel the electron at P in that particular direction along the position vector. Yes, now the same thing, it's a little bit off center, so let me point it. Yeah, now what happens is if I choose another point B which is diametrically opposite of B, this point B will also try to repel the same electron at P by the same force but with a different direction, right? Now because of that, what happens? Now because of that, these two forces would have each force will have a component which is perpendicular to the axis, right? And each force will have a component that is parallel to the axis. You see the components along the axis, they support each other, and the components perpendicular to the axis will cancel each other. That means we can just ignore or cancel these, right? Now what we have is a stronger electric field directing along the axis and away from the ring. Simple. Now if I choose a point Q, right, not on the axis, right, then what happens? Now understand, this particular point Q will be closer to some of the charges, right, will be closer to some of the charges of the ring and will be farther from other charges of the ring. But the charges that are closer to point Q will have a larger force because of the inverse square property of the Coulomb's law than the charges which are farther away. So essentially it is the charges closer to point Q that will win, right? So what kind of force will they create? Now of course they will repel, right? They will repel, and the repulsion would be slanted like this a little bit. Yes or no? Right? So, or you can say, right? Okay, now understand, if it's inside here, look at this. Similarly, if you choose a point R here, let me write it here, the point R here, the field will be like this. So same thing happens. So basically, you see, this is the kind of forces you will see. This is the kind of forces that you will see at on electrons at different points, within the cylindrical space defined by this ring. Now understand, imagine if I have multiple such rings coaxially placed close to each other, they will basically create a cylinder. And what happens to the electrons inside the cylinder if it's a metallic cylinder that has a lot of free electrons? And somehow I create a stable charge distribution on the surface rings. Then what will happen? They will squeeze the electrons towards the axis, right? They will squeezed electrons move towards the axis and away from the rings. Yes or no? Simple. So basically it will try to pump these electrons in the axial direction in one direction. You might say, sir, why is it moving to the right? Why is it moving to the left? Well, it would also squeeze electrons to the left also. But then let's just look at only one part, because as the discussion will go, I will create a positive ring on the other side, on the right. So the electrons will tend to go from negative ring to the positive. Imagine if I have a positive ring here. The positive ring what will it do? It will try to attract the electrons. So basically the electrons will be squeezed from the negative end to the positive end, right? From the negative end to the positive end. So basically the free electrons in the entire volume of the cylinder, defined the cylindrical cross section of the wire, tend to move as part of a current. Is it understood now? Now imagine if I have a cylindrical wire, and now the next segment of our discussion is, let's say I have a cylindrical wire and now in this cylindrical wire, imagine if I just injected some electron of charge negative q. The moment when I inject it, it's a metallic wire. So what happens? These electrons will try to repel each other and try to stay as far away as possible from each other. So basically these electrons will distribute themselves on the surface, the cylindrical curved surface, right? So in that case, this distribution will be uniform, and we know that in a steady state, in a steady state, and when I say steady state, it means no net motion of charges, right? When there is no net motion of charges in this cylinder, like once I inject some electrons, they will basically take a very, very small amount of time, a few nanoseconds, to redistribute themselves. But once that is achieved, you will have a steady state, and in a steady state, internal electric field of a metal or conductor will be zero. You can also prove that using Gauss's law, but we are not going to get into mathematics here. We're just trying to understand the concept theoretically. So in a steady state, you see there has to be no net field inside the cylindrical wire. So all the charges that I just injected, all the electrons that I have just injected, will eventually distribute themselves uniformly over the cylindrical surface. Understood? Now when it happens, can I just cut this cylindrical surface into tiny rings? Right? Can I just cut this into infinitely many tiny rings, elemental rings? Right? When I do that, what happens? I get a structure like that. That's just the previous case. It's just that electrons will still not move inside, because the electrons do not have anywhere to go. And why would they go? Right? There is no net field actually being inside, right? There is no net field inside, so the internal electrons will not move, the surface electrons will not move, right? It's simple, right? Because ultimately the electrons residing here they can't move outside. The electrons residing here, they can't move outside. So essentially, since the ends are sealed, the electrons are not going to move at all. Even if there is a squeezing force, right, on the free electrons, but the electrons are fully packed there is no chance to move. Now what happens? How can I create a motion? So basically, I'll have to create a gate for them, right? So when I do so, what do I do? Understand. In this case, I use a battery. Right. I use a battery. Let me just delete all these electrons. I'll have to redistribute. Imagine if I'm using a battery. This is the positive end, this is the negative end. The moment when I connect this battery, the moment when I connect this battery like this to my wire, so what happens? The battery creates a positive end on the left, right? And a negative end on the right. So what it essentially does is it basically creates a positive distribution. It sucks some electrons on the left and it supplies the same number of electrons to the right. Right? When it happens, you see there is a charge difference that has been created. When there is a charge difference that has been created, you see a lot of electrons are here and a very there is a high scarcity of electrons on the left and there is a high concentration of electrons on the right initially. The moment when I connect, right? The moment when I close the switch. Imagine if I have a switch for your visualization. Imagine if I have a switch S. The moment when I close it, that's suddenly what happens. There is a positive charged ring that is created on the left and a negatively charged ring that's created on the right, right? And then there is a, now what happens because of the charged imbalance, the surface charges, right? The surface charges will try to move, the surface electrons will try to move to the left. Yes, on the entire surface, the electrons will try to move to the left to balance the charge imbalance. All right. However, the imbalance cannot be removed as long as there is a battery, right? As long as the battery is connected, the imbalance cannot be removed. Why? Because whatever is the amount of electrons that just move to the left, immediately the battery is going to replenish the same amount of electrons to the right hand side, right? So basically this flow will continue on the surface. Now what happens inside the wire? It's the same thing as we have discussed in the previous case. Now because along the axis every ring is going to, on the axis, along the axis of the wire, the electrons are going to push along the axis and the rest of the electrons are going to be squeezed towards the axis and towards the left. And this will continue. This is going to continue. And why is this? Why exactly is this flow of electrons inside the volume of a wire happening? It's happening because of the charges or the charge distribution on the surface, right? These electrons are influenced by the charge distribution on the surface of the wire. You might say that on the surface of the wire the electrons are also moving. Yes, they are moving. However, since they're moving right on the surface, their motion is not going to stop as long as the battery is connected. So you can visualize, you can treat them as if well, these charges, there is a constant charge distribution. Even if the electrons are moving, you can still say that the electron distribution on the surface remains a constant over time as long as the battery is connected, right? And that's exactly how the electrons flow. Now what happens if I bend the wire? Now imagine if I bend the wire. Imagine, why just in a circle? Imagine if I have a wire and I've bent it in the S shape, let's suppose. Right? And then I have connected a positive and here negative. So basically I connect the battery and I connect the battery here. So you have a negatively charged center there. Well, doesn't make a difference. You still have rings, infinitely small rings. And how many of such rings? Infinitely many, right? So essentially what happens is the net force, or you can say inside the wire, because it's not in a steady state, right? So even if it's a metal and the internal electric field of a metal has to be zero, but then it needs a steady state. But you would not have a steady state as long as you have a current. So the electric field, right? The electric field inside will be always tangential, right? It will always be tangential to the wire at any given point. The electric field inside the wire, if it's a DC direct, when the current is driven by a battery, then it is always tangential internal field, and that is created by the surface charge distribution. That's why you would have seen that if you disturb a current carrying wire without making it lose its connections with the source, as even if you bend it, like deform it, give it a different shape, straighten it, suddenly make it a circle, or make it a helix, or bend it into an S shape, you see there is no difference. It doesn't make any difference on the current that flows in it. And this tangential internal field is basically responsible for tangential tangential current density vector. What is the current density? The current density J, I will small j if you want to write. Current density J is basically the amount of current flowing divided by the at any given point. The current density will be the area of cross section related to that point right here. So current divided by the area of cross section multiplied by n cap. N cap is the normal to the area, right? Not along the current. Simple. So this tangential internal field is responsible for the tangential current density vector, which is created by the surface charge distribution. So far, so good. So that's now you've understood why by changing the orientation or the shape of a wire, we don't actually make a difference to the current that the wire carries. But understand here, the charges flow inside a wire, inside the volume of a wire, right? Only when it is DC. However, when you go to AC, how much charge inside its volume will flow depends on the frequency of the AC, which we will discuss now. Right? Now, understand one thing. Whenever you look at any current carrying wire, right? That is for a DC supply. It will be just a single solid wire, right? No serrations, nothing. It will be a single solid wire in DC. Why? Because we need more volume, right? Because most of the charges flow inside the wire. But when you talk about alternating current, so AC on a wire. Now let's understand. Once again, I will try to draw a wire here, cylindrical wire, right? And we will see, will electrons still move inside the volume of the wire, right? Okay. Now in this, look, let me take just a small cross section, right? Let me take a very small cross section here as an example, right? In this cross section, there are charges flowing, right? There is an electric field that is let us suppose I have initially, right, let's suppose I have a positive end on the left and negative end on the right, and we say that the electric field is, let's suppose, somehow passing through. You will say, sir, the electric field should not always be all parallel to the axis. Fine. Let's say that the electric field is here. So, and the electric field is like at the top, it will be more like this, and gradually it will squeeze off. Right. Okay, fine. So this field maintains itself like this if it's a DC, right, direct current. What if there is an AC? When there is an AC, the EMF changes, and as the EMF changes, the electric field changes. Now the electric field E is a variable, right, with frequency F. Whatever is the frequency of the AC supply, the electric field will also have the same frequency. Anyways, now what happens? Now understand, if the area of cross section of this wire, of this area of cross section of this particular segment is A. Now we know, you know Maxwell's law. Now understand here. So depending on, there will be, since the electric field is a variable, depending on whether the electric field is increasing or decreasing. Let's say the electric field is increasing, right, to the right. Let's suppose it's increasing to the right. Right, let's say it is increasing to the right. In that case, right, if you apply the right hand thumb rule, you will see that the magnetic field, a tangential magnetic field, will be generated along the boundary of the area, circular area, so it will have a circular boundary. Now these magnetic field are induced magnetic field, right? These magnetic fields are induced magnetic field, right? So with this induced magnetic field, so that is in accordance with Maxwell's law, which is, that integration, the loop integration of V dot dl, that is, if you integrate the magnetic field along the loop of the periphery of this cross section, that must be equal to mu naught epsilon naught, assuming that the that is like what you consider that the permeability, you can just consider this as mu epsilon naught, mu epsilon, right? Imagine you would say, sir, why mu naught epsilon naught? There is no vacuum, there is probably some metal here. Well, in that case, it's just mu epsilon naught d phi e by dt. That is the rate of change of the flux of the variable electric field. So if the electric field is a variable, then its flux will also change, and depending on its flux, an induced magnetic field, depending on the rate of change of the flux of the electric field, an induced magnetic field will be generated. Simple. Now it's an AC. Now the higher F will mean that stronger magnetic field. Yes or no? Clear? So now here understand, imagine, let us understand, since it's positive and negative, there is an electron. Imagine there is an electron that is trying to go in this direction with some velocity, drift velocity v, right? So what happens? Understand, this is an electron negatively charged, it's right, and it is trying to move in this direction. At that point, the magnetic field, let's suppose the magnetic field is in this direction. So this is V, right? This is V and this is B. Now what happens? We know the force on a charge, moving charge inside a magnetic field is QV cross B, right? So in this case, it's an electron, which means it will have the force will be of opposite direction. So V cross B, if you do, right, understand, if you do V cross B, right, if you do V cross B like this, then the force, as you can see, once again, for cross products you can use the right hand thumb rule. The thumb points towards out of the plane, right? in any way, if it's an electron, the force will be in this, getting into the plane, right? The force on this electron. So basically what will happen? The Lorentz force, right, on the electrons moving in the wire, right, will eventually push all the electrons towards the surface, right? All the electrons will be pushed towards the surface, right? So stronger magnetic field means more electrons will be pushed. Weaker magnetic field will be means less electron will be pushed. So you will see, we can understand now that in in AC supply, right, in AC supply, higher frequency will push more electrons to the surface of the wire. So much so that in India we use a 50 hertz supply, right? In US we use 60 hertz supply. So in these frequencies, 50 hertz or 60 hertz, almost all flowing electrons exist on the surface. Almost all the flowing electrons exist on the surface of the wire. And that is why you will see that, if you talk about a DC wire basically will be a whole wire. But when you talk about an AC wire, because in AC, right, electrons flow on the surface of the wire, so we need more surface. And DC, electrons flow inside the wire, so we need what? We need more volume, right? DC wire, we need more volume. But in AC wire, you might have noticed that you would have tiny, tiny wires, right? You know, you have tiny, tiny wires, many, many wires packed together. You see, many, many wires packed together in AC. It's never a single solid wire. It's a collection, is a bunch of, tightly wound, thin wires, a lot of thin wires. Why? Because when you use multiple wires and, wind them together to make a large wire, so what you have is more surface. And this is called skin effect. What I said is, this thing is known as skin effect. Skin effect is the effect due to which the internal free electrons get pushed towards the skin of the conducting wire in case of an AC. So I think this has, and again, when you bend a wire, you might be thinking, right, if it's a straight wire, it's fine. But if I bend a wire, well, even if you bend a wire, you can see the distribution of charges, like the ring-like distribution of charges, right, coaxially for the wire. There's, that happens, what do you call, elementally. That happen infinitesimally. So the rings are so small that, the bending of the wire has no effect on it. So essentially, these rings automatically redistribute, readjust their position so that they will always produce an electric field that will be tangential to the wire, whether it's AC or DC. However, the difference is in DC, most of the electrons flow inside the wire, and in AC, most of the electrons flow outside the wire. Exactly how much, that depends on the frequency. So I think that probably has cleared your doubt. So if so, let me know in the comments. And if you have any other doubts, you can follow the link in the video. Go to thephysicist.in/ash to ask your doubts. And if you need another topic on which I should be making a video, please mention it in the comments. Thank you very much. See you in the next one.